So, we have seen in last class that considering the relativistic relativity, the energy level now depends on n and k. So, what will happen? This we have seen that I have discussed that for a particular n value. So, if n equal to 1, then k will be equal to 1, n equal to 2, k will be equal to 1 and 2, n equal to 3, k will be equal to 1, 2, 3, right. So, corresponding, if I draw these orbits, so also here we have seen that from here we can see when n equal to k means here n equal to 3, k equal to 3, then a equal to b, then a equal to b means it will be circular. Okay. So, whenever n equal to k, then that will be circular orbit, and for other cases it will be elliptical orbit. So, if I draw just so we have a nucleus, So, for n equal to 1 we will have this first orbit. So, that will be basically circular, So, that is n equal to 1. N equal to 2, I will get next orbit, n equal to 2, I will get next orbit. So, for n equal to 2, k equal to 1 and k equal to 2. So, k equal to 2, n equal to 2. So, that will be again circular. So, let us draw this next orbit. Next orbit is not perfectly circle, but okay. So, more or less it is circle. So, this is n equal to, so this n equal to 2 and k equal to 2. So, now n equal to 2 and k equal to 1. So, it will be orbit, elliptical orbit, but its but its a will be same, length of a will be same, because as you remember that I wrote a equal to n square a h by z and b equal to n k a h by z, right. So, n a does not depend on k, but b depends on n and k. Okay. So, for n equal to 2, k equal to 1, a will same, but b will change, b will shrink, it will decrease. Okay. So, this whatever this a value here radius. So, here you will get basically shifting of this one, keeping the same. So, this basically I will get say basically one can draw like this. So, this kind of elliptical orbit one will get. Okay. So, keeping the a same, b decreased. Okay. So, and keeping this nucleus at one of the foci. So, this will be for n equal to 2 and k equal to 2. Okay. So, this way now we go for n 3. So, again for k 3 it will be circle, and this there will be other 2 elliptical orbit. So, that way one can draw the orbits for hydrogen atom, considering the Bohr-Sommerfeld model. Okay. So, now here one thing I have not mentioned, that here I have used alpha. What is alpha? What is alpha? Alpha is basically is constant. Alpha is constant, and so alpha is constant. Alpha is constant, and it's E h cross by it's called fine structure. So, this alpha value is I think it will be E square by C h cross. It's a constant, E square by C h cross. Okay, E square by C h cross. So, E is constant, C is constant, H is constant, H cross is H by 2 pi. Okay. So, if you put value, so it's basically one can write VB by C also one can write. So, what is VB? VB is basically velocity in Bohr radius. Electron when it is in Bohr radius n equal to 1 for original Bohr energy. If you look there, their expression, if you look there, expression of V velocity. So, it varies with n. Okay. For n equal to 1, whatever the velocity is, that is called n equal to 1 Bohr orbit, and electron in Bohr orbit, what is the velocity? That VV. Okay. So, that is again constant all the time, it will not change, universal constant. Okay. So, Bohr orbit is taken as a universal orbit, it cannot change. So, whatever the velocity energy, that is also constant all the time. So, this value comes is basically 1 by 137. Okay. It comes 1 by 137. Okay. So, that's alpha is a constant, and it's very very smaller than 1. So, very small quantity. Okay. And it is called fine. It's called fine structure constant. Why it is called fine structure constant, that I can explain. So, alpha is called basically fine structure constant. Because you see here for a particular orbit or particular nucleus. Okay. So, this energy, how much energy will decrease or increase. Okay. From one energy level to another energy level, one orbitals to another orbitals. So, that alpha decide, value of alpha decide. Okay. For a particular n, for a particular k value. Okay. For a particular n, for a particular or two successive k value, what will be the energy difference? So, that is decided by this term. Okay. And this term basically it's this value will depends on the alpha square. Okay. And alpha square is very very small, you know. So, it's you can say this 10 to the power minus 2, square of it will be 10 to the power minus 4. Okay. So, this contribution is it's 1/10,000th times of this value, whatever here. Okay. Or whatever the energy, original energy. So, that will be that contribution, increase or decrease. So, that will be, it will be by factor of 10 to the power minus 4. Okay. So, change energy between these levels. So, if I draw now for hydrogen, just let us take one spectral lines H alpha. Its wavelength was around I think around 6,000. Okay. So, now these lines came from n equal to 2 transition between n equal to 2 and n equal to 3, n equal to 2 and n equal to 3. Now, these lines are now due to this or according to Sommerfeld model. So, n equal to 2 means k equal to 1 and 2. So, this energy level will split, it will be basically 2 energy level for k equal to 1 and k equal to 2, that already I have discussed. So, k equal to 1 is lower than this k equal to 2. So, this separation is very small. Okay, this separation is very small because this factor control this separation. Similarly, for n equal to 3, what I will get? N equal to 3, I will get again 3 lines. One is this, so this k equal to 1, then I will get k equal to 2, then I will get another level k equal to 3. Okay. So, earlier it was one line, means for n equal to 2 one line energy level and n equal to 3 another energy level. Transition between these two levels was given a spectral line. Now, this energy levels are splitted into higher than the 1 levels, and now if we consider transition. So, looking at the experimental result, so transition rule, selection rule was considered that transition only possible when it will satisfy the change of k delta k, it is plus minus 1. Okay. So, this called selection rule. Selection rule again, it was hypothesis, it was considered that all transition is not possible. So, only it follows some selection rule. So, it was considered that this transition will be only for this case delta k equal to plus minus 1. For other case it will not be possible. So, here it just in ad hoc basis it was considered, there is no explanation, only looking at the experimental result it was considered, but from quantum mechanics we will see later on that it comes, these rules comes automatically. So, now we have to take it as a ad hoc on ad hoc basis. So, if I consider these rules, then if I start from here, so k equal to 1 and here k equal to 1. So, if transition, this transition is not possible because delta k equal to 0, that is not allowed, but k equal to 1 to k equal to 2, this transition is possible because this it is plus minus 1. If you consider this is the initial and this is the final. So, final minus initial, if I consider this way, final minus initial, so it will be plus 1, okay, 2 minus 1 plus 1. So, this transition is possible, fine. So, from this level it is not allowed, only this is allowed. So, I will get one spectral lines, and then if I start from here k equal to 2. So, here k equal to 2 it is not allowed, delta k equal to 0, k equal to 2 and this k equal to 1 it is allowed because 1 minus 2 is a minus 1. So, final minus initial, in that way if I consider. So, this is allowed. So, this is allowed, this is allowed. Okay. And then from k equal to 3, k equal to 2 it is allowed, again it is minus 1, okay, delta k is minus 1, and k equal to 3 to k equal to 1 is not allowed because this difference is minus 2. So, selection rule do not permit. So, only 3 transition is possible, other transitions are called forbidden transition. So, from here it is not allowed, it is forbidden, and from here this is forbidden, okay, and then only this is allowed, and now from here it is allowed, but this is forbidden, okay, this is forbidden. So, what we are getting? We are getting this now. This is basically, it's according to Bohr model, it's the one line is now composed of 3 lines. They are very, well, the difference are very small. Difference are very small. So, now it is split into, it should split into 3 lines, but experimentally, as I told that no, it is not 3. This H alpha line, it is composed of 5 lines. It is composed of 5 lines. It is composed of 5 lines. 1, 2, 3, 4, 5 lines. Okay. So, even Sommerfeld model or Bohr-Sommerfeld model, partly it can explain the splitting of the energy level, but it's cannot explain fully. We need more transition. Okay. So Bohr-Sommerfeld is that model is, again, it is not yet correct model or full model, which will be able to explain the experimental result, but still some more lines we need, means we need more quantization. Okay, we need more quantization. So, this result is indicating that whatever 2 quantization we have considered and 2 quantum number we got, this principal quantum number and angular quantum number or azimuthal quantum number. So, there are some more quantization. So, that one has to consider, one has to find out. Okay. And also it was observed that when we apply electric field or magnetic field, then each spectral line without electric or magnetic field, each spectral line, so it may not, it is not this line, whatever here we are getting. So, each of them, each spectral line without applying electric or magnetic field, whatever the spectral line, you are looking at a particular spectral line. Now, just if you switch on the electric field or magnetic field, means your sample, your atom is under electric field or magnetic field, then this lines is splitted, okay, into more number of lines. Okay. So, when you are applying magnetic field, due to this magnetic field, these lines are splitted, and this effect was discovered in, I think, 1896, more exactly I did not remember, but I think 1896 this effect was observed by Zeeman, and it is called Zeeman effect. It is splitted into more lines, So, here I have drawn 3 lines. So, in Zeeman effect, again two types of Zeeman effect. One is called normal Zeeman effect, another is called anomalous Zeeman effect. Normal Zeeman effect, Okay. What is that? When you apply a higher field, Zeeman observed that when you apply higher field, in higher field, any spectral line splitted into 3 lines, any spectral line splitted into 3 lines. Okay. So, it is independent of this what is the origin of the spectral line, that does not matter, but any line splitted into 3 lines at higher magnetic field. Okay. So, that effect was called normal Zeeman effect, but later on it was found that if you use weak magnetic field, if you use comparatively weak magnetic field, low magnetic field, so this splitting of a spectral lines into few number of spectral lines. So, that number is not same for all spectral lines. So, it depends on the origin of the spectral lines. Okay. So, it splitted all the time, it is seen that it is splitted more than the 3 lines, splitted into more than the 3 lines. Okay. So, in some cases it is split into 6 lines, some cases it is split into 4 lines, etc. So, it is more than 3 lines at weaker field, weaker magnetic field. So, that is called, so if under weaker field, so if you see that it is splitted into more than 3 lines, it can be 5, it can be 4, it can be 6. So, then that is called the anomalous Zeeman effect, anomalous Zeeman effect. Okay. Zeeman effect. Okay. So, normal Zeeman effect and anomalous Zeeman effect. Okay. So, I define that. So, what is the origin, that we do not know yet, we have to find out. So, here 2 clues is there. One is that this from Sommerfeld model we are getting more lines, but it is not sufficient yet. We get more, even more lines, number of lines. So, another is when we are applying the magnetic field, then we are getting one line is split into more lines. Okay. So, tendency towards the more lines. So, there should be more splitting of the energy levels, and splitting of the energy levels only possible from the quantization. So, more quantization we need. Another aspect, as I mentioned, that this even if you apply electric field, then also this spectral line splitted. So, that effect. So, this is for magnetic field, this for magnetic field, that is H, this for magnetic field, and for electric field. And for electric field, if we apply electric field, then one line splitted into more lines. Okay. So, how many lines, again it depends on this origin, it is not same for all spectral lines. So, when we apply electric field, so whatever effect we are getting, so that called Stark effect, Stark effect. Okay. So, these are the event was experimental observation was available, and then people start to search more quantization of the system. So, we need more coordinate. So, then next, I think this Sommerfeld itself, he pointed out that here quantization, whatever we have considered, that it is elliptical orbit, two coordinate we need, r and theta, and they are periodic function of time. Okay. And so considering these 2 coordinate, what we are getting? We are getting basically planar motion. So, orbit ellipse in a plane, we are getting orbital motion in a plane or planar motion. Okay. Now, in which plane if I consider the planar motion, so in which plane atom is 3 dimensional, say spherical shape, okay. So it is in space. Now we are considering the in spherical shape. Now we are considering a or ellipsoid. We are considering an orbit, okay. So orbit is on a plane, okay. So now which plane we will consider? So whether it is in this plane, or whether it is in this plane, or whether it is in this plane, okay. So any plane it can, so answer is so far it can be any plane. So direction of the plane can be any, okay. There is no restriction on the direction. So angular motion of the electron, right, it has angular momentum. So direction of the angular momentum is basically perpendicular to the plane, right. So if it is in this plane, so it is perpendicular to the plane, this direction of the angular momentum is perpendicular to the plane. Now this, it can be different plane, and this direction of the angular momentum will change, right. It can be in any direction in space, it can be any direction of the space, okay. So now here I think this is called space quantization. So it is considered that no, it cannot be in any direction, it cannot be in any direction, it cannot be any plane, okay. So there is a quantization. So it is quantized, this direction is quantized in space. So it cannot take any direction, it can take, it is again quantized, it can take this direction, and then these are not allowed, then it can take another direction, okay, then it can take other direction. So all other direction, all directions are not permissible, these directions are quantized, and this is called space quantization. So to take space quantization, one has to fix reference direction in space, right. One has to fix reference direction in the space, okay. So since applying electric and magnetic field, okay, then we are seeing the splitting of the spectral lines, okay. So that is why the direction of the magnetic field or electric field, okay. So I have atom or system of atoms, okay. Now I am applying electric field or magnetic field. So I am applying magnetic field in a particular direction. Now with respect to this direction, if I fix this direction, take as a reference in space. Now with respect to this, what are the planes, orbital planar motion of the electrons are permissible, okay. So this so this motion we have considered r and theta, okay. Now with respect to this, okay, these planes, this fixed. Now if this is the plane or this is the plane, okay, in this plane this orbital motion. Now if I take angle between this reference direction or magnetic field direction and my plane direction, okay, if it is a plane direction, or I think it is taken generally the plane direction means perpendicular to the plane, okay. If this is the plane direction, means plane is like this, perpendicular to the plane. So now angle is, if we consider phi, so angular momentum p phi, angular momentum basically p phi, p seat, I think if I consider p phi, okay. So that p phi will be basically p theta cos phi, okay. So in space momentum, if in space now if you take this projection along this direction, so it will be p theta angular momentum, its projection on this fixed direction, this will be p theta cos phi, okay. Now it is telling that if I write p phi, that equal to p phi. So, now it is telling that p phi is quantized, that p phi is quantized, and this will be equal to some h cross. Earlier we have used n, then k, here it is used m or m phi, okay, m phi h cross, okay, m phi h cross. Here one can take the same quantization integration integral. So, p phi, now again it is angle direction phi angle, right. So, this that integration will give you 2 pi. So, equal to n phi h, okay, divided by 2 pi. So, n h cross. So, you will get n phi h cross, but that we have taken m phi. So, in general n phi we write this m h cross. Okay. So, this m is called magnetic quantum number. This m is called magnetic quantum number. This m is called magnetic quantum number. Magnetic quantum number. Okay, magnetic quantum number. So, so we have now another quantum numbers. So, now is 3 quantum numbers. So, now with taking this again, we will try to explain whether we can get from H alpha, whether we can get 5 lines, whether we can get this normal Zeeman effect, anomalous Zeeman effect, and the Stark effect, whether we can explain or not, that we will see. So, I will stop here. In next class I will continue. Thank you.